Nicolas he's here at University of Toronto. He works on security and privacy of machine learning, surprisingly. And he's done a lot of really cool stuff across the board on that, adversarial examples, privacy, some stuff on machine learning recently. And, besides his research, he's done a lot of really cool things for the community. He's founded this new conference, StatML, on secure and trustworthy machine learning, which has a call for papers, which is now out, deadline in September, October, around there. And everyone should submit. It's going to be right here in Toronto. He's been recognized a lot for his research. He's got this Sloan. I think he's got at least 2 iClear best papers, at least 1, probably 2. But yeah, without any further ado, I'm going to let him take it away and talk about how to steal machine learning models.
Thank you, Gautam. Can everybody hear me well in the back? No? You're good? Some people say yes, some people say no. So, all right. So yeah, thank you so much for the kind introduction. Also, thank you, Gautam, for helping us with StatML. We really appreciate that. So today I thought I'll talk about something a little different from sort of usual topics like adversarial examples, differential privacy, and go into a threat vector we've been exploring over the last couple of years with a lot of people here at Vector, which is how to steal machine learning models, but also how to prevent these attacks. So Gautam made the good point that hopefully we'll try to find solutions today against all of these attacks. You'll see that here we made partial progress, but I don't think we can claim victory yet. So what do I mean by stealing machine learning models? Essentially what I'll work with in this talk is a setup where the adversary is given access to an oracle, which essentially reveals the prediction of a machine learning model that they don't have white box access to. So you can think of this as one of your machine learning as a service APIs. You submit an input, it responds with a label or with a representation of that input. And now you're trying to leverage access to that output to basically reproduce the model locally, to have a copy of the model on your own machine. And so what we've first looked at is in the context of computer vision. So if you think of your usual image classification tasks, sort of benchmarks, what the first key observation is that stealing machine learning models is made a lot easier by all the progress that has been made in the machine learning community and learning with little supervision, right? So if you take things like semi-supervised learning, what that means is if your adversary has access to unlabeled data, then now they only need to label a fraction of these data points before they can learn a copy of the model that performs the same task, okay? And so this is something we looked at, for instance, in this paper with techniques like mixed match. We see that an adversary that previously had to submit tens of thousands of queries to extract an image classifier can now do hundreds of queries because they have access to both this unlabeled data and these semi-supervised learning techniques. Now, the challenging part is to extract machine learning models when you don't have access to a proxy distribution that is similar to the distribution the machine learning model was trained on. And so in these cases, you have to essentially figure out how to synthesize queries that will be useful to submit to the victim model that you're trying to steal, to then learn something about its decision boundaries. And so to give you an example how to do this, here in this work, we leverage a setup that is similar to how generative adversarial networks work to essentially learn a generative model that will first synthesize useful queries to make to the victim model. And then we, at the same time, learn a copy of that model using something that would essentially play the role of the discriminator in the usual GAN setup. So the way that it works is that you have this generator, it takes random noise, outputs queries which are sent to the victim model, and then we compare how the victim model responds to these queries compared to the student model, which is essentially the copy of this model that we're trying to train. And so this gives us the loss that we would then like to backpropagate to figure out which inputs the generator should create such that it maximizes the difference between the victim and the student model, right? Because these will be queries that we should be submitting to the victim model such that we learn the most about what the student model hasn't extracted yet. And so if you had differentiable access to the victim model, this would be very easy. You could just backprop through this whole thing. Because typically the victim model is something you're trying to steal, you don't have access to its parameters, we essentially have to use finite differences to recover approximations of the gradients, and that allows us to train the generator. And so this is a successful strategy in the sense that you can take something, for instance, victim model trained on CIFAR, you can extract it without any initial knowledge of the distribution that it was trained on. The downside is, of course, that this takes a lot of queries, especially because you don't have access to the gradients of this model. You're not estimating through finite differences. So to give you an order of the number of queries here with access to unlabeled data, we're in the hundreds, and here we're in the millions without access to any data prior to starting the attack. Okay, and so now you may wonder, do these kinds of attacks work on more modern architectures where the model is outputting representations rather than specific predictions like what is the label of that input? You can use basically very similar setups. The only difference comes in the loss that you're using to basically compare the output of the victim encoder and the encoder that you're trying to reproduce. Yeah.
So what's your notion of loss between?
Yeah. So here we're basically looking at a loss that is comparing these two models. Yeah. Yeah.
What case is the loss with respect to some?
So here we're just computing this over the inputs that we're outputting. So we're just computing an average case. I see. The success is basically that we have the same average case accuracy on the test distribution for both the victim and the student model. Exactly, exactly. So that's what we're trying to achieve.
And the test distribution doesn't get repeated?
No.
So that's the goal.
That's right. That's a heuristic because we don't have access to the exact distribution that the model was trained on. Okay, and so here this is sort of a similar conclusion, but for self-supervised models. And so what I want to get at here is that essentially if you're revealing the output of a model's sort of a model that is hidden, you can't really prevent an adversary from extracting it because essentially you're giving the output of the function for any input the adversary would like to know that output for. So if they make enough queries, eventually the adversary will be able to recover some approximation of that function. Yeah, sure.
Is the theoretical guarantee of it or is it practical?
This is practical, yes. And so what I want to cover in the rest of the talk is essentially, can we do something to first try and detect if a copy of the model is really a copy of the model that you have trained yourself, okay? So imagine you have different models that you are able to interact with, for instance, through APIs. Now you're trying to figure out, is this model that I'm interacting with a copy of the model that I have trained and made available, right? So you could imagine, for instance, a competitor may have stolen your model, is now profiting from giving access to this copy of the model. So the first strategy that we looked at, which is something that a lot of people in the community have looked at, is watermarking, where here the idea is that we'd like to essentially insert an unusual behavior in the model's decisions so that we can then claim that the model is ours when we basically predict what the model will output on these unusual inputs. Okay, so these are the watermarks. The way you can think about it is like if you have an image, you add a little square at the bottom left of the image, and you know that when you do that, the model will predict, for instance, the class 7 all the time. This is not necessarily tied to the underlying task that the model is trying to solve, but because you've watermarked the model, you know you've trained it to respond in this way. Once someone copies your model, you would hope that if you query it with a watermarked input, it will respond again in the same way. Okay, The problem is with this strategy, if you look here before, during, and after training at the representations, is that if you do this naively, the model will learn different clusters in the representations to recognize inputs from the legitimate distribution and inputs from the watermark distribution, okay? And so what this means is if an adversary is just interacting with your watermark model and wants to remove that watermark, all they have to do is perform some form of distillation where they only query your model on the legitimate task that the model was trained to solve, and they'll never learn the behavior that the model has learned to recognize the watermarked inputs. Okay? So if we want to prevent this form of attack, we have to instead add a penalty during training to encourage the representations of the legitimate inputs to be entangled with the representations of the watermarked inputs. And what that means is essentially that we'd like to use the same kinds of features to recognize inputs from the legitimate distribution and inputs from the watermarked distribution, okay? And so we can use entanglement penalties to do this. And so this will affect the training in this way, where you can see that now the same cluster in the representation space is used to recognize both legitimate and watermarked input. The downside of that is, of course, now to be able to have this behavior, you have to sacrifice some of the model's performance on the legitimate distribution. And so there's this sort of trade-off between the robustness of the watermark and the performance of the model itself. So the next question we asked ourselves, given this limitation, is, do we really need to insert watermarks in the first place? Right? One thing we asked ourselves is, maybe the training data that we use to create the model is in itself some form of a watermark. And here, of course, the person that is training the model in the first place has full knowledge of the training set. And so to be able to tell whether another model has derived knowledge from your own training set, what we realize is there is a number of results in the privacy literature where people have basically developed attacks against machine learning models to decide whether or not a particular point was used to train that machine learning model. And this is known as membership inference. And the way that it works is essentially, there are, of course, more sophisticated attacks now, but it's essentially doing some form of confidence thresholding, in the sense that if the model is more likely, if the model is predicting with high confidence, it's more likely it has trained on that input. And so what we realize here is that we can take all these membership inference attacks and now flip their use case. Rather than use them as attacks, we can use them as a defense, in the sense that as a model trainer, we have knowledge of our training set, so we can use some of these points and perform membership inference on models that we suspect may have been stolen from us, okay? And what we'll see is that membership inference will be more likely to succeed if the model was indeed a stolen copy than if it was not. And the nice thing here is that membership inference usually has very low success rate. It's very hard to run membership inference attacks on a single particular point. But the good thing here is we have access to the entire training set. So even if the attack is just slightly more successful than random chance, as long as we aggregate the results over enough samples, we're able to get more confident that indeed the model was a stolen copy of ours. And so here in this paper, essentially we implemented this strategy. We also looked at ways that we can approximate the signal that is needed for doing membership inference without having access to the model itself and without access to its confidence. For instance, you can take a point and perturb it multiple times and look at how many times you have to perturb it to get a proxy of its confidence if you're able to observe the label flipping at the output level. So this is essentially the idea here. And you can do something similar. You can apply the same strategy of dataset inference in models that don't output labels. Essentially, you're trying to estimate the density of the training, of the representations on the training distribution, the test distribution, and you'll see that when a model is stolen, that the density on the training distribution will be higher than on the test distribution, whereas for a model that is independently trained, those will be indistinguishable. So now, before I finish, I want to discuss one more thing, which is essentially, can we slow down a model stealing attack rather than only detect it after the fact? So I've started by telling you it's somewhat unavoidable model stealing attacks because you're revealing the model's outputs. Unless you're degrading the utility for the legitimate user, you can't really expect to prevent them. What I've shown you in these defenses with watermarks, dataset inference, is you can hope to detect that model stealing has happened after the fact. But now can you try and essentially increase the cost of a model stealing attack so that you make it, you decrease essentially the incentive that the adversary has to perform this kind of attack. And so here in this setup, what I'll show you is how we can augment this usual API design where you have unlabeled data, you submit it to the victim model returns the labels directly in a way that increases the cost for adversaries, but not for legitimate users. And so the idea is to take here an intermediate step where the victim model is not going to directly return the label as users are making predictions, but is instead going to try and estimate how much information is leaking through the answer to that query. So by revealing this input-output pair, how much information am I revealing about my model? And then the defender is going to use this to generate a cryptographic puzzle whose difficulty is calibrated by how much information is estimated to be revealed by answering this prediction. And so what this means is that then the user or the attacker has to solve that puzzle before they get access to the label. And so if you calibrate the puzzle in such a way that it's harder to solve when the query is revealing a lot about your model, but easier to solve when it's not revealing a lot about your model, then you can get to a point where the attacker has to spend a lot more compute or has to essentially just wait for longer before they're able to steal your machine learning model. And so that changes a little bit the incentives. And so the way that we did this is by, again, leveraging techniques from privacy. There are a lot of connections between privacy and model stealing. And in particular here, we used some techniques that we came up with when we were working on Pate, which is an approach to learn machine learning models with differential privacy guarantees. And so what this allows us to tell is essentially when we have a query, how much information we are reviewing is estimated by the privacy budget of that specific query, okay? And so what we found is that if you look at here, the accuracy of a set of queries as a function of the privacy estimate, what we're seeing is that all the adversaries are essentially increasing their privacy faster than a legitimate user for a given sort of test performance. And so what this means is that if you calibrate the puzzle to the privacy budget, then the adversary will face a much larger privacy budget. So we'll have to solve a much more complicated puzzle than the average case test user, which is just sampling from the test distribution. And that makes sense because the model stealing attacks are designed to learn as much as possible with as few queries as possible. Okay? And so, yeah, sure. Yeah. No. It's basically, no. Otherwise, we would have a big problem. And so just to show you quickly the practical impact of this approach, this is the overhead that a legitimate user is paying by basically solving these puzzles before they have access to the predictions. So we'll take this overhead. It's perhaps not trivial, but it's not significant. And this is here a first attack where you can see now the overhead much more significant, which means essentially the adversary has to spend more time, more compute before they get the same degree of accuracy. And then if we take an attack that has no access to the underlying data distribution, then because it has to make so many queries, in this particular case, this is the data-free attack that I presented on the right of the first slide, then the increase in the time to run the same attack with the same model performance is a lot more significant. Yeah.
The text that you are comparing here text without awareness of such existing such a pattern.
Yes.
Maybe if I'm aware that
yes.
there is such a design different patterns.
Yes. 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 We've looked at that, and basically in the limit, what you have to do is, and we discussed that in the paper, is you have to take basically. You need to make queries that will have minimal privacy budget. And so these are essentially getting you back to the test distribution. So in the limit, it makes sense. Your attacker is losing basically its advantage compared to just a legitimate user that is sampling from the test distribution. Oh, there is another question. Uh-huh. No, sorry. Yeah. Yes. 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 So basically here there's another variable, which is the number of queries that the attacker is making. And so here we're just visualizing accuracy as a function of time, but this is drawn by essentially having a varying number of queries. And it's just, if you make certain queries, they increase your time and also increase your accuracy at the same time. Yeah. Yes. So we don't need to solve the puzzle. We basically just verify the solution to the puzzle. Yes. Yes. Basically, it's hard to find the solution, but it's easy to verify it. Yeah. Oh, like if you have a Sybil adversary? Yeah. So essentially, what will happen there is they will still have to each pay the cost of their queries. So it will just add up back to what we have. We thought about this because you could estimate basically how much information is leaking with, at the same time, keeping some sort of longitudinal information. But we try to avoid doing that so that we can handle these attacks that are sort of distributed across multiple accounts. And then I think here there is sort of probably in sort of a practical deployment, you would want to basically combine this with some more sort of classical security mechanisms to also try and identify adversaries that are colluding, so that you can also further increase the cost of these attacks. Because there are ways you can identify, sort of, for instance, if you have an API, accounts that are suspicious or too new, for instance, that may have been created to launch these kinds of attacks. So you could imagine incorporating that in the defense itself. We haven't done it here because it's sort of orthogonal. Yeah. Yes. Am I out of time?
No, you have still a ton of time. I just wanted to make a meta announcement for the sake of the people online and also people in the back of the room. It would be good if either the people asking questions can pick up this thing in front of you, press it so that the light turns green, or if the speaker can repeat the question in case they forget.
Sure.
Cool.
Sounds good. So I just want to cover a little bit more. Oh, okay, great. So here, one of the takeaways from this line of work is essentially, if we want to increase the cost of model stealing, we essentially have to reverse engineer the training dynamics of the attacker. We have to understand how does an attacker make specific queries in order to train their copy of the model at the smallest cost. And I'll come back to on that particular connection in the next set of slides. I think here there are some limitations with how we evaluated how much information is leaking from the queries. Pate is not going to be a good fit for all possible settings. So there is a lot of, I think, value in looking at how we can estimate how much an input-output pair is worth. And this is a problem that is not new. If you look at the field of active learning, for instance, this is sort of a question that's been studied for a long time. And so I think there's value in looking at that. There is also this maybe philosophical question of what it means to own a machine learning model. Is it any different from owning the data that was used to create this machine learning model? If you look at the approach that I discussed with the dataset inference approach that is based on doing multiple times membership inference, essentially it's sort of hinting at the fact that the way that you sort of identify that a model was a stolen copy of yours is essentially by proving you own the data that was used to create your own model. Okay, and so there's this, in this setting with these models that we've experimented with, it seems like the two are not so different. But now that people are putting in a lot more compute in training their machine learning models, and you might argue the choice of the architecture is also possibly something very sensitive, and it really creates this open question of, do we need to differentiate model from data ownership? And I think just talking a little bit to legal scholars about this, it's really not clear how to translate these mechanisms that we developed in something that sort of maps to what sort of intellectual property law would allow you to protect. And so I think this is an interesting question to think about. So just briefly to conclude this connection that I mentioned to training dynamics, I think overall, just to open up the talk, and I'm happy to discuss this in the breakouts and so on later, I think in the area of trustworthy machine learning, there is really not enough work looking at the training phase of machine learning models and trying to, in particular, understand how we converge to the particular model that we eventually release. And so recently in my group, we've been looking at this particular question and trying to understand what can we infer from having knowledge of the intermediate models that were basically explored by the training algorithm. So if you think about your stochastic gradient descent, it's going to go through a sort of a long sequence of models before it arrives at the model that you are eventually going to release. And we found that there are a lot of problems where we've simply been ignoring all this information and just trying to secure the last model that is being deployed without leveraging the information that the training run is giving us. And so a very simple example is in this problem of selective classification, you're essentially trying to decide, should I respond to a particular query or not, in the sense that if I respond, do I think I'm likely to make a correct prediction? Otherwise, I can simply abstain and not make a prediction on this particular input. And so here, what I'm trying to do is maximize coverage, which is essentially saying maximize how many queries I respond to, while at the same time responding to these queries with very high accuracy, okay? And so what we found, for instance, is if you just look at the intermediate checkpoints that you achieve during training, it gives you a lot of signal about which inputs you will make correct predictions on. So for instance, here I just give you a very simple example with a very clear test input. You're essentially going to observe, this is based on empirical observations. What we observe is that if you look at the class that is being predicted by the intermediate check, we found that it converges very early on in the training to the class that is predicted at the end of training. Whereas for a lot of the ambiguous inputs that you would make an incorrect prediction on, we found that there is a lot more oscillations in the class that is being predicted during training. And so this gives you a very simple heuristic that you can use to basically decide which inputs to predict on. You can say, if you observe you have this convergence as early as possible in training, that means these are the queries that you should probably respond to. And in the case you have oscillations, you should more likely abstain on this query. Yes, Shai.
Okay, yeah, but the problem is that what you're saying now is that I'm throwing away all the advantages of a big model of many iterations, and I'm just predicting like a model that just did few iterations. Because anytime I'm not doing like the few iterations, I'm saying I'm not certain, I throw it away. So the whole advantage of many iterations goes to the waste with this attempt to be confident.
I'm not sure. So essentially, if we compare this kind of approach to other approaches for selective classification that look at the last model and, for instance, try to decide which queries to respond to based on the logits of the model, or by regularizing the model to also be able to predict sort of how confident it is, this approach either matches or outperforms the performance. So at least in the setting where we have this sort of accuracies versus coverage question, it doesn't seem like sort of relying more heavily on the earlier models harms you in terms of performance.
But did you compare it to the behavior of a very few iterations model? And
just predicting with the very few.
Yeah.
I guess that would still not tell us which inputs to predict on.
No, but the accuracy should now become like the accuracy of a few iteration model.
Sure. So I guess we use a different metric to basically get a sense of what the baseline is, which is we essentially try to derive what is the optimal coverage we can achieve given the performance of the model that is trained at the very end. So I think that kind of goes at the same question. I can show you the thoughts in the paper. I think it answers that question. So very briefly, and then I'll take questions. So there are a couple of examples I wanted to give of this work. So we looked at this in the non-private setting. We also looked at this in the private setting, and it has an advantage in the private setting in that you are essentially obtaining all these models for free in terms of privacy, because the way that the privacy analysis, for instance, in differentially private stochastic gradient descent is done, it gives you access to the intermediate models at no extra cost in terms of privacy. And so you can run this approach to decide which inputs to classify with your privacy-preserving model. And that essentially allows you to recover some of the utility drop that you observe at full coverage if you're able to abstain for some of the inputs. Although it's not sort of immediately obvious why that should work, because also learning with privacy should make it harder for you to distinguish training and test points. So it also harms this approach in some ways. And then another example of why sort of trying to understand training dynamics is interesting, again, in a privacy setting, what we found is that if we try to, and I'm not going to explain the approach, but just briefly mention the results, which is if we try to understand how, basically to characterize the fact that gradients in training are often very similar, whether or not you include a particular point or not. In practice, you can very, very often obtain very similar gradients from lots and lots of different mini batches. Then what we found is if we are willing to analyze the privacy of our algorithm in a way that is data dependent, then having access to this analysis of the training dynamics allows us to basically prove a much tighter bound on the leakage of that privacy preserving algorithm. But again, this comes at the cost of an analysis that is not dependent on the data that you're running the algorithm on, which is a caveat. Okay, so with this, I want to, I guess, briefly advertise StatML. Gautam did this for me, so here's the deadline, October 11th. And I also wanted to say all the videos from this year are online, so feel free to look this up if you're interested. And then I also want to thank all my sponsors and some of my students here who are involved in the papers that I discussed today. And I'm happy to answer more questions if you have more. Thank you.
Cool. Thank you, Nicolas. We have time for some questions. Be sure to use the microphone when asking. Go ahead.
Thanks. Nice talk. So I want to talk about the last week you discussed this agreement over the duration of the training. So can you say more about how that relates to the confidence of the models as they progress through training? So, for example, is it the case on the bottom, if you evaluate on that blurry image, that throughout training, each of the models remains confident, even though it's predicting different, is it giving you more information than the confidence?
Yeah, so we compare it to basically looking at the confidence of the last model. You're right that I don't know off the top of my head if we could further improve the approach by also looking at the confidence of the intermediate models. I don't think we've looked at that, but that would be a good next step. Yeah. Yes.
I want to ask about the membership inference that you said could be a tool for identifying what models are stolen. I want to ask how reliable you think it is when the training data sets are close. Like, what if a model is trained, it's not stolen, it's legitimately trained on another model, but it's on another data set is very close to the original data set you have?
Yeah.
Are there particular data that you look for? Do you look for if outliers are there for membership inference, or how reliable is it?
Yeah. So this is a very good question. So essentially, the approach I discussed with dataset inference, it will smoothly degrade the more there is overlap between the training set of the victim model and the training set that the sort of adversary had access to in sort of a legitimate way from a different source. So for instance, to give you an example, if you have models that are pre-trained, that makes it a lot more difficult to run dataset inference, because now these two models, even though they were then fine-tuned on different data sets, they also have the pre-training set in common. And so that sort of will make it harder for you to separate sort of to threshold, is this my model or not? Right. And so in this setting, essentially, you're back to something that is closer to the watermark, which is that you're trying to identify which of my training points are unique to my basically machine learning pipeline, and which data points do I think others might also have access to, right? So that actually makes it a lot more difficult to do dataset inference, for instance, in language models, because they're also crawled. These different models are all learning from data that is crawled from some of the same websites. So then you have essentially a lot of overlap in the points that they're trained from.
Right. Yeah. And sorry, I realized it's not off. And is there did you try any algorithm to find those data that is kind of particular to your own model? As I said, an example would be the outliers that you have in the data, or? No,
we haven't tried to have sort of a algorithmic approach to select the points to perform dataset inference on. But that would be I think that would be a good idea, to basically try to automate the process of. It would be interesting to evaluate if you can do this and then look at sort of different. The problem is you need to look at different setups where people might have shared sort of access to data. So basically, there are lots of ways that you can imagine creating copies or derived models. So for instance, if you're trying to prune a model, if you're trying to distill a model, in addition to just the very data that you used to create these models, there's also the way that you're sort of integrating knowledge from a previous model into your model that you have to take into account and evaluate. Yeah. So for this agreement-based work, have you considered what's the impact on fairness? Because if you just, it could be that the minority records from the minority subgroup are the ones that have a lot of variation, and those are the ones that are suppressed. So that's one, and the second is. Hold on, one question at a time. Okay. So was that about the agreement? Yes. Yes. Okay. So you're absolutely right. There are some implications to fairness, and in particular, we looked at this briefly. We haven't written any publications about this, but I can point you to some other work in the community about this particular aspect. But you're right. Essentially, there will be points that you are rejecting because you haven't sort of converged on early on in training that will impact certain fairness metrics. And so there might be a tension there. It might also be a way to algorithmically identify points that are part of essentially certain subgroups that are characterized by that fairness metric. The second is the impact on privacy risk, more specifically membership inference, because now you're just outputting high confidence predictions. So on one end, it seems like you could make it more risky, but on the other side, you could also be giving out more false positives. So have you considered that? How? So yeah, so you're asking basically if membership inference is unreliable because of the way the model was trained, what happens to data set inference? Yeah. Sorry, I can't hear you there. Yeah. Oh, sorry. So the same agreement-based approach, will it make it more vulnerable to membership inference, or do you have more false positives? I guess, this is a good question, because I guess you will, yeah, you're essentially giving more signal by abstaining, in the sense that the points you abstain on are less likely to be points that you've trained on, so, or that are similar. So that probably does leak. I guess it's not systematic, because we can still use the approach in a setting where the model is trained with privacy guarantees. So I think it's hard to answer that question generically for all the points, but you're right that we might be able to use that additional signal as an input to our membership inference attack. Also, it might be the false the test records, despite not being in the training data set, are the ones which are high confidence. They're the ones that are outputted, and in which case false positives will rise. Well, yeah, what we're trying to do in this approach is essentially to try and figure out which of the test points could have been points that we trained on, essentially. And to answer your question, essentially, another thing to keep in mind is in the dataset inference paper, one way we validated this is by trying to run dataset inference, for instance, on models that are trained with differential privacy. And so if you train with differential privacy, you will eventually decrease the success of membership inference if your privacy guarantee is sufficiently strong. And so what that means is that you're bringing the success of the membership inference closer and closer to random chance. And so at the same time, if the defender still wants to use dataset inference, they essentially have to make a lot more queries. So they're revealing more of the training set. And so at some point, there's this trade-off of how much you're willing to reveal about your training set by essentially querying the models to run the membership inference attack, and sort of how much you're gaining from knowing that they've stolen your model.